Hello everyone, my name is Hadila Bujamus and I am making a video today about synaptic transmission. In order to understand synaptic transmission, first I'm going to talk about the structures in the neuron. And the neuron consists of the cell body here and dendrites sticking out of the cell body. And the dendrites are in the 3D, cover the cell body in 3D, and the entire dendrites are called dendritic arborization. And here's the cell membrane, which is the lipid, consists of the lipid bilayer. And here's the axon helic, and this is the axon, and then the axon terminals. The axon terminals are also called terminal buttons. The axon is covered by myelin sheath, and myelin sheath is the insulation layer of the axon. The myelin sheath consists of Schwann cells, and Schwann cells cover the entire length of the axon, but in between the Schwann cells there are the axon is exposed to the extracellular environment, and between each cell to the next cell, these areas of the axon are called nodes of Ranvier. So nodes of Ranvier are the space between each cell of the Schwann cells. Now I'm going to move on to a 3-neuron network, and in a 3-neuron network I have cell A here in red, and cell B in black, and cell C, which shows the dendritic the dendrites, and they are on the cell body but it's not shown here. So our story starts with an event that starts in cell A, in which a neurotransmitter is released in the synapse between the presynaptic membrane of the axon terminal and the postsynaptic membrane of the dendrite. So the neurotransmitter is released in the synapse, and this black box is enlarged here, and this shows the presynaptic membrane, which is the axon terminal button, and in relation to the postsynaptic membrane, which is the dendrite on the dendritic arborization of cell B. So when a neurotransmitter is released, 4 things can happen to this neurotransmitter. It can be taken back into the presynaptic membrane by a process called reuptake, or it can be degraded or metabolized by enzymatic degradation by enzymes in the space which is filled by interstitial fluid. Another thing that can happen to the neurotransmitter is it can dissipate away, it can just float away. Now the 4th option for a neurotransmitter, this is the option that we are interested in, is actually binding on a receptor on a dendrite, which is part of the dendritic arborization of cell B. So when this happens, this is where our story continues on with the synaptic transmission. And this box here is enlarged here, and it shows the neurotransmitter in relation to the receptor. And this receptor is called a ligand-gated ion channel. So there are 2 parts for the receptor: a binding site for the neurotransmitter and a pore which allows the ion to go in. Now without binding to the binding site, the ion pore is closed, that's the part of the receptor. Now we have a neurotransmitter that is bound to the binding site on the receptor, which changes the conformation of the receptor. When the conformation changes, the pore opens, and now sodium can go inside the cell. So this is the outside of the cell, and this is the inside, and this is the plasma membrane of postsynaptic membrane of cell B. Now sodium goes inside the cell from the higher concentration from the outside to the inside. Now I want to focus on why sodium goes inside the cell. And now I'm going to talk about the ionic concentrations and the difference between the outside and the inside in the neuron. we have this box represent the inside of the neuron, and this is the outside, the interstitial fluid. Now the ionic concentrations are different with different ions. For here there's a big Na, which is sodium, and it represents the higher ionic concentration of sodium outside compared to the small concentration inside. And also here we have potassium, K+, which has a higher concentration inside than the outside. We also have chloride that has a higher concentration outside compared to the inside. Now another thing about the ionic concentrations or the inside of the neuron is that when everything is added up with everything inside the neuron, the net charge is actually negative. So the net charge of the inside of the neuron is negative. Now this is called the resting membrane potential with the different ionic gradient, and the inside of the cell, the resulting resting potential is negative 70 millivolt. Now let's go back to our receptor and the relation that when sodium goes inside. Now when this pore opens, because it's bound to the neurotransmitter, sodium goes inside. And I want to talk about that sodium goes inside the cell. This is the arrow showing sodium moving inside the cell. And that happens because of two forces: the electrostatic pressure and osmosis. For osmosis, because ions or molecules would like to go down their concentration gradient, and that's the reason sodium goes inside the cell from higher concentration to a lower concentration. Also, the electrostatic pressure is because the inside of the cell is negative, then sodium, which is positive here, is attracted to the negative inside of the cell. And this is the and these are the forces that allow sodium to go inside the cell. Now, sodium is inside the cell, as we have said here. Sodium is inside the cell. What happens is we can actually measure them. We can measure this movement of the ions across the membrane, and the measurement is done by an oscilloscope, and it can measure the membrane potential difference in volts as time goes on. So this graph shows the millivolt on the y-axis and milliseconds on the x-axis. Now when we are at the resting potential, at the resting membrane potential, it's at negative 70 millivolt. Here is negative 70 millivolt. And we said that a neurotransmitter is bound to the receptor, the pore opens, sodium goes in, so the cell becomes more and more positive. And when that happens, here we are at the level, at the position number 2. So 1 was the resting potential, and now at number 2. Number 2 here, when it's sodium is going inside and the cell becoming more positive, this is called an EPSP. An EPSP stands for excitatory postsynaptic potential. And when that happens, then the cell becomes more positive. Now let's say there is enough neurotransmitters bound to many receptors and many pores open, and if we sum all these excitatory signals together, we sum all these EPSPs together, and they are summed at the axon helix. Here it is summed at the axon helix here. Now if the voltage reaches negative 65 millivolt, we are here at number 3, at position number 3. We reach the threshold. If the threshold is reached, then something happens in the neuron. In the axon helix, voltage-gated sodium channels open up. So they're opened by the change in voltage, and when the voltage reaches negative 65, because the summation at the axon helix, because of all these EPSPs, then the voltage-gated sodium gated channels open up. When they open up, sodium floods inside the cell, because, as we said, the two forces acting on sodium. And sodium goes inside the cell, so the cell becomes even more and more positive to reach the maximum level here. So this upward movement, this rising phase of the action potential is, I've numbered it here 4. It's called depolarization. So this is depolarization of the membrane. And then the sodium keeps moving inside the cell until it reaches equilibrium. So that means sodium on the outside equals to the sodium in the inside. And when that happens, actually this causes the voltage gated sodium channels to close up, and at the same time potassium voltage gated channels open up. When that happens, then two forces act on potassium again. Osmosis, it wants to go outside, down its concentration gradient because of osmosis, and also because now the cell is so much positive. See here, the maximum is at plus 35. There's electrostatic pressure for potassium to go outside the cell. It's repelling all this positivity inside. So potassium leaves the cell because of the two forces. Now when potassium leaves the cell, so the cell becomes more and more negative, and this falling phase of the action potential is number 6, is called repolarization. And repolarization continues on, but it doesn't stop at -70. No, it keeps going down further at the position number 7. And number 7 is called hyperpolarization. Now, because the hyperpolarization occurs because there's enough potassium leaving the cell that it actually the membrane potential becomes hyperpolarized. Or I'm sorry, the membrane becomes hyperpolarized. Now, in order for the membrane to reach the resting membrane potential, again here at number 8, sodium potassium pumps, they act to restore the normal resting potential ionic concentrations across the membrane. So sodium is large on the outside, small on the inside. Potassium is large on the outside, potassium is small. I'm sorry, potassium is large on the inside and potassium is small on the outside. So here we have reached, this graph is describing the ionic movements and the different channels that open and close that gives us one action potential. Now, so we are here. Let's review. We have an event that happens in A. It releases the neurotransmitter and in the synapse, and it binds to the receptor, and the binding of this ligand gated channel which allows sodium to go inside. Now sodium goes inside and depolarization, EPSP happen, and enough summation at the axon helix then triggers the voltage gated channels to open up. Now the action potential now propagates down the axon, and this propagation down the axon is called saltatory conduction, and that happens because of the myelin sheath, because of all these Schwann cells, and at the nodes of Ranvier. So here an action potential is it's moving down the axon, and when it reaches a node of Ranvier, the axon is exposed to the outside environment, to the interstitial fluid, and the axon has sodium voltage gated channels, and when the voltage is right, negative 65, because the potential is moving down the axon from the inside, then these channels open up and sodium goes inside the axon, and then the membrane becomes depolarized. So we recreate another action potential at the first node of Ranvier, and this repeats itself, this jumping from node to node, and this is the process that the action potential propagates down the axon. Now when it propagates down the axon of cell B, it reaches the axon terminal or the terminal button, and then it releases what happens here is so this is the bigger picture here in the synapse, and what happens is the action potential reaches the terminal button, and which allows calcium to go in. Now when calcium goes in, it triggers these vesicles that contain the neurotransmitter to move along and merge with the membrane. Now when these vesicles merge with the membrane, they release the neurotransmitters into the synapse. And again, our story starts over again by the for the neurotransmitter and the binding, and another action potential is regenerated. That's my summary for synaptic transmission, and I hope you found my video useful and helpful, and thank you so much.